We're in sort of a good news, bad news situation right now with where we are with the concordance cosmology. The good news is we have a model that fits all the data. 5% of the universe ordinary matter, 25% dark matter, 70% dark energy. Since 1998, when we first found evidence that the universe is accelerating, this idea has been tested by many, many different ways. It keeps coming out passing the tests. It seems as if the universe is accelerating just as the first supernova observations indicated. The bad news is we don't understand it. The dark energy part in particular is very exotic and outside our ordinary experience. In fact, the dark matter part is also very exotic. 10 years ago, I would be giving a set of lectures just on dark matter, and that would also seem very exciting and exotic and interesting. These days, the dark matter seems almost prosaic compared to the dark energy, which is something truly different. So clearly we want to do the best we can to test this idea, to figure out whether or not this hypothesis, 70% of the universe is some smoothly distributed, persistent form of energy density, is in fact correct. We want to use that hypothesis to make predictions and then go out there and test those predictions. The most obvious test that we can think of is the one that I mentioned in the last lecture, the geometry of space. So here is once again the Friedmann equation, the equation derived from Einstein's theory of general relativity that governs the relationship between energy density and the curvature of space in an expanding universe. What we're saying here is that the energy density is given by the sum of a contribution from the expansion and a contribution from the curvature of space itself. It turns out that the right amount of dark energy you need to make the universe accelerate is also the right amount of dark energy you need to make the universe spatially flat. In other words, to satisfy the Friedmann equation with k, the spatial curvature term, being 0. That is a testable prediction. We can try to imagine measuring the curvature of space itself. So in this lecture, we're going to go out and actually measure the curvature of space on very, very large scales. In other words, what we're doing is the same kind of thing we were doing when we were using gravitational lensing to measure the weight of a galaxy or a cluster of galaxies. What we were doing then was letting light rays go by a cluster or some other massive object, and we were mapping out the local geometry of space near that gravitating object. Since Einstein tells us that space and time are warped and bent by the presence of matter, mapping out the geometry of space and time is a way to tell how much stuff there is. So we can do that very straightforwardly with individual clusters of galaxies. Now we're going to do that with the whole universe. We're going to look at how light propagates through space to measure the geometry of all of space all at once. That's how we can be sure that we're not missing anything. When you're looking at individual clusters, it's always possible in principle that there's something outside. When you look at the whole universe, you're guaranteed to find everything that there is. So here are the possibilities for what the curvature of space could be. Remember what this means. This means that since the universe is uniform everywhere, there is a certain single number which tells us how much space is curved. That number could be positive, it could be 0, or it could be negative. That number is the curvature of space. It's related to omega, the density parameter. Omega is telling us what the total density of the universe is divided by the critical density, in the sense that when omega is 1, the universe is spatially flat. When omega is greater than 1, it is positively curved, like a sphere. When omega is less than 1, space is negatively curved like a saddle. You can think about the directions of curvature of space bending in different directions. Now, the curvature of space is something like many other things in cosmology. It is hard to visualize the reality of it. Whenever you're drawing pictures, representations of the curvature of space, the best you can do is draw a two-dimensional version. The actual space in which we live is three-dimensional. As far as we know, the three-dimensional space in which we live is not embedded in any bigger space. It is all there is. So when we're talking about the geometry of space, we're talking about the intrinsic geometry of space. We're not talking about how it looks to an outside observer. We're talking about things you can do when you are inside space to measure its geometry. When we say the geometry is flat, we mean that the kind of geometry that Euclid invented thousands of years ago is the right kind to describe space on very large scales. Euclid looked at tabletops as a paradigm for where to do geometry. He would draw right angles and triangles, come up with different laws at how geometric shapes fit together. We want the three-dimensional version of that. So we want to draw triangles and straight lines and circles within a big three-dimensional space, look at their intrinsic properties. So there are different intrinsic properties that are telling you how space is possibly curved. The most obvious one is the angles inside a triangle. If you draw a triangle on a tabletop, or a triangle just in a three-dimensional space that is flat, no matter how you draw that triangle, no matter how it's oriented or no matter how big it is, when you add up the angles of those three angles inside, you will always get 180 degrees. The way to think about the statement, space is flat, is to translate it into the statement, every single triangle I can draw anywhere in the universe has angles inside that add up to 180 degrees. If space is positively curved, a similar statement would hold true about triangles, but it would say that the angles will always add up to more than 180 degrees. We can visualize that by imagining a sphere, drawing a triangle on the surface of a two-dimensional sphere. It would be the case that the angles inside add up to greater than 180. So we have the three-dimensional version of that. We're imagining that space itself in which we live is a three-dimensional version of a sphere. Just like on a regular sphere, if you start at one point and walk around, you will eventually come back to where you left. In a three-dimensional sphere, in a universe with positive spatial curvature, if you walk off in one direction, you will eventually come back to where you left. It will take you billions of years, but you would eventually get there. Negative curvature, then, means that you once again draw big triangles. In a negatively curved space, every triangle you can draw has angles inside that add up to less than 180 degrees. That's the kind of thing you can do. It's not the only thing you can do. A famous postulate of ordinary Euclidean geometry is the parallel postulate. It says if you start with two straight lines and let them go, two parallel lines, if they're initially parallel, they will always remain exactly parallel. That is to say, if they're initially having the property that the distance between the two lines is a constant, not changing as you go past the lines, that will always be true no matter how far you go. That is a postulate of Euclidean geometry. It is not a necessarily true fact about the world. If we lived in a positively curved space, two lines that were initially parallel would eventually come together. That makes perfect sense. Thinking about a sphere, you can draw two lines as parallel as you want. If you trace them down, they will eventually hit each other somewhere. In a negatively curved space, meanwhile, you start with two parallel lines, you follow them down, and guess what? They're going to peel off. They're going to be becoming more and more far apart. That is a thing that you can imagine empirically doing in space that would reveal whether space was positively curved, negatively curved, or flat. So we briefly touched upon something called the flatness problem in actual cosmology. The flatness problem has sort of an informal version and a formal version. The informal version of the flatness problem is the universe seems to be close to spatially flat. When you calculate the actual density of matter in the universe, now putting aside dark energy for a bit, if you knew only about the matter, you would say that we've reached 30% of the critical density necessary to make the universe flat. 30%, as these things go, is awfully close to 100%. It makes you think that we're almost there. So there's this feeling that you're just missing something. You should be exactly flat if you knew what everything was. That's the sort of informal version of the flatness problem. But there's a more formal version of the flatness problem, a statement that is a little bit more quantitative that drives home exactly how surprising it is that the universe is close to being spatially flat without exactly being there. Basically, there's a statement that the universe doesn't want to be flat. If the universe is a little bit non-flat, if there's a little bit of curvature to space, the amount of curvature becomes more and more important as the universe grows. So if you live in an old universe, the universe should be very curved, if there was any curvature at all. You can see this roughly from the Friedmann equation once again. The Friedmann equation is relating the energy density to the expansion rate and the spatial curvature, so you have three terms in that equation. But remember that for the energy density, we have very well-defined rules about how the energy density changes as the universe expands. For ordinary matter, or for dark matter, for any particles that are slowly moving compared to the speed of light, as the universe grows, the density goes down and the volume goes up, so the energy density goes down exactly like the number density goes down. Particles just become more dilute. For radiation, the energy density goes down even more quickly because the number density goes down, space becomes bigger, but also every single particle of radiation is losing energy. So we have very well-defined rules that tell you how the energy density changes as the universe expands. There's also a well-defined rule that tells you how the spatial curvature changes as the universe expands. You can imagine blowing up a balloon. The balloon, when it's very small, looks very curved. As it gets bigger and bigger, every little cubic inch on the balloon looks flatter and flatter. In the same way, curvature dilutes away as the universe expands. However, when you plug in the numbers, curvature dilutes away more slowly than the energy density in matter or radiation. To be technical, the curvature goes like 1 over the scale factor squared. The energy density in matter goes like 1 over the scale factor cubed, and the energy density in radiation goes like 1 over the scale factor to the 4th power. So as the universe gets bigger and bigger, as the scale factor grows, the energy densities in matter and radiation fall off more rapidly than the contribution to the spatial curvature. So imagine that there is some non-zero spatial curvature in the very early universe, that the term k in the Friedmann equation is not exactly 0 at early times. Even if it's fairly close to 0, the relative importance of that term compared to the importance of the energy density in matter or radiation grows. We live today in a very old universe. The universe is 14 billion years old. It's had 14 billion years for the spatial curvature to overtake and overwhelm the energy density of matter and radiation. But it hasn't. That is the technical statement of the flatness problem. In order to get a 30% of the critical density universe today in just matter and radiation, the difference between being absolutely flat and being curved in the early universe had to be incredibly infinitesimal, had to be very finely tuned to just the right tiny, tiny, tiny amount so that today it would be comparable to the energy density in matter and radiation. This seems like an unlikely situation. That is the flatness problem. So 30% of the critical density, the amount that we've found in ordinary matter, is a weird number to have. That's why before we found the dark energy, theoretical physicists who were very convinced by this were thinking that omega matter, the contribution of the total density of the universe just from ordinary matter plus dark matter, had to be 1. They were believing that the universe had to have the critical density since it was so close. It would make no sense to not quite go all the way. They believed in a flat universe. But at the end of the day, you can believe whatever you want. It's not going to make you any money. You got to go out there and look. So how do you actually measure the spatial geometry of the universe? Ideally, you want to do what Carl Gauss did when he was inventing the concepts of non-Euclidean geometry. He actually made a big triangle, and he measured the angles inside. So we want to make a big triangle in the universe. Of course, we can't travel to distant galaxies stringing lasers or a piece of wire from one place to another. We have to take celestial objects as they're given to us and use them to construct a big triangle, add up the angles inside. So one way to do this is if we had a standard ruler. A standard candle is something whose brightness we know, and so the further away it is, the dimmer it will look. A standard ruler is something whose size we know. So the further away it is, the smaller it looks. So a standard ruler is just as good a way to measure distances to objects as a standard candle is. The reason why you don't hear as much about standard rulers is because there just aren't as many of them. There aren't that many objects in cosmology or in astrophysics whose size in miles across you actually know ahead of time. Galaxies, stars, different astrophysical objects appear in different sizes. However, imagine that you not only had a standard ruler, but imagine that you knew how far away it was. Imagine you had some object whose size you knew and whose distance you knew. Then you would think, I must be able to figure out exactly how big it will look. That would be true, assuming that you knew the geometry of space. The angular size that that ruler will take up, if you know how big it is and you know how far away it is telling you the geometry of space. If it has a certain angular size, 1 degree across, in a flat universe, then in a positively curved universe, it will look bigger than 1 degree across. That's because the angles that you're subtending from the light rays that come from you to the object or vice versa are pulled together by the positive curvature. So they can start out bigger and they will end up at the different angles of your standard ruler. Similarly, if you have a negative curved universe, that ruler which would have looked 1 degree across is now going to look smaller than 1 degree across. However, this is of course asking a lot. We're asking not only that we have some object whose size we know, but we want to put that object in some place and we know exactly how far away it is. How lucky do we have to have some object that has a fixed size and a known distance? Well, we got lucky. The universe provides us with exactly that in the form of the temperature fluctuations in the cosmic microwave background. We already talked about the cosmic microwave background, the leftover radiation from the Big Bang. The cosmic microwave background is a snapshot of what the universe looked like about 400,000 years after the Big Bang. Times earlier than that, the universe was so hot that individual atoms were ionized and the universe was opaque. Light could not travel very far before bumping into an electron. After 400,000 years, the universe had cooled down enough that electrons and nuclei had gotten together. The universe became transparent and light traveled unimpeded through the universe. So we see what the universe was looking like about 400,000 years after the Big Bang. The universe at that early time was much smoother than it is today. Today, the universe is smooth on large scales, but on small scales, we see individual planets, stars, galaxies, clusters. At very, very early times, the universe was smooth on essentially all scales. It's the tiny deviations from perfect smoothness at that early time that grew under the force of gravity into stars and galaxies and clusters. So if you look at the cosmic microwave background, observing not only that it exists, but also delicately measuring the temperature of the cosmic microwave background at different points in the sky, you're measuring the imprint of those primordial fluctuations in density. Here is the classic picture of the cosmic microwave background from the WMAP satellite. It is an all-sky picture. It's the whole sphere that we look at when we look at the sky, projected onto an ellipse in this image. And what you're seeing here is just the tiny fluctuations in temperature. These fluctuations from place to place are only 1 part in 100,000. The blue spots are a little bit cooler, the yellow and red spots are a little bit hotter. This is telling us where the density fluctuations were located on a sphere 400,000 years after the Big Bang. So we can learn a lot from these density fluctuations. We don't know any theory that predicts a precise place for where they should be. We don't ever expect to have such a theory, but we do know the statistical properties that they should have. We already in an earlier lecture talked about the fact that the properties of these splotches on the microwave background, hot spots and cold spots, provide evidence for dark matter. That's because what you have in the primordial universe is a hot plasma that is experiencing acoustic oscillations. You have an ionized plasma, but in some regions it's a little bit more dense, in some regions it's a little bit less. Under the force of gravity, a region is going to collapse under its own gravitational field and heat up. That will increase the temperature fluctuation in that region. It's now hotter than it used to be. The dark matter, of course, continues to fall in, but the ordinary matter bounces because of pressure, and it becomes less hot than it used to be. That's also a fluctuation, but now it's a lower temperature than a higher temperature. And it goes back and forth exactly like that. Let's ask the question, what size would you expect the largest amount of fluctuation to be? The point is, if a region that is going to collapse is very, very big, it doesn't have time to collapse in any appreciable way. Its temperature fluctuation is going to be whatever it was stuck with in the very, very early universe. If it's too small, the region collapses and expands and collapses and expands and bounces back and forth and gets damped. So eventually it settles down into a configuration that is not very fluctuated, that is not very different from the surrounding plasma. However, there is one particular length for which a region has time to collapse and heat up, become fairly substantial in terms of the difference that it has in temperature, but doesn't have time to bounce back yet. That will correspond to a physical size in light years of the age of the universe in years at the moment when the microwave background is formed. In other words, since the microwave background is a snapshot of 400,000 years after the Big Bang, regions that are 400,000 light years across will have the greatest amount of fluctuation in their temperature. So we have a prediction. We have a prediction for at that moment, in the cosmic microwave background, we know how big the most noticeable hot spots and cold spots should be. They should be 400,000 light years across. Furthermore, we know how far away the cosmic microwave background is. Using the Friedmann equation, using some theory for what the universe is made of, which we have, we can predict the distance from here, us today, to there 400,000 years after the Big Bang. In other words, we have all the ingredients for making a big triangle. We have a standard ruler on the microwave sky. It's the hot and cold spots with the largest amplitude, and they are predicted to be 1 degree across if the universe is spatially flat. In other words, if the universe is spatially curved, positively or negatively, that's like taking the map that you would predict in a flat universe and either magnifying it or shrinking it. So these are the data that you have from WMAP. You can compare them to the prediction. And what is the answer? The answer is that the universe is spatially flat. This is in fact not first found by WMAP. There were other experiments that found this. The boomerang experiment from Antarctica was actually the first to make a precision measurement of the size of the most dominant fluctuations in the cosmic microwave background. They all knew ahead of time what they were looking for. If it was 1 degree across, that would be evidence that the universe was spatially flat. This was in the year 2000, soon after dark energy had been discovered, but when people were still very excited, although skeptical. They wanted to know, was this picture hanging together? So the boomerang experiment and other experiments following up on it looked for fluctuations in the cosmic microwave background, 1 degree across. That's exactly what they found. In other words, the microwave background is telling us that the universe is spatially flat, that the total density of stuff in the universe is the critical density. It fits perfectly with the concordance cosmology of 5% ordinary matter, 70% dark energy, 25% dark matter. So exciting this was that in 2003, when WMAP came along, Science magazine declared it to be the breakthrough of the year, even though what they really did was just say we didn't make a mistake in 1998. In 1998, the acceleration of the universe was the breakthrough of the year. That suggested the concordance cosmology. In 2003, WMAP came along and said, yes, that's right. This crazy universe with 5%, 25%, 70% is really the universe that we live in. That's sufficiently surprising that, again, that was the breakthrough of the year. One thing to take very seriously is the fact that the microwave background tells us the total energy density of the universe. So if you just take evidence from the cosmic microwave background that the total energy density is the critical density, and you add that to the evidence from clusters of galaxies, ordinary galaxies, gravitational lensing, that matter only adds up to 30% of the critical density, then you don't need to mention the word supernova to be convinced that there's something called dark energy that is 70% of the universe. It's just 100% minus 30% is 70%. In other words, whether or not we have a correct theoretical understanding of the physics of type 1a supernovae, whether or not the two supernova groups did a good job in explaining their error bars and collecting data that was reliable, you're still forced to the conclusion that dark energy exists. The constraints that we have right now overdetermine the kind of universe in which we live. You can't wriggle out of the conclusion that there's a lot of dark energy just by being skeptical of the supernova results. So the place we are is that we're stuck with a universe in which 70% of the energy density is dark energy. We now must face up to the same kind of problem that we had with dark matter. Given that there is this stuff, what could it be? Let me just foreshadow a little bit by saying what the simplest possible candidate for dark energy would be, and that is something called vacuum energy. Remember that the two important properties we know dark energy has are that it is spatially uniform, more or less the same in every location in space, and it's persistent in time. The density the amount of energy per cubic centimeter isn't changing very much for the dark energy as the universe expands. So the simplest idea for something that is more or less smooth in space and more or less constant in time is something that is exactly constant throughout both space and time. In other words, a form of energy density that is inherent in space-time itself. Just the statement that every little cubic centimeter of space contains energy, whether there's any stuff in that cubic centimeter or not. So here is the closest I could come to an artist's representation of what this idea, vacuum energy, really looks like. You imagine you take a little cube of completely empty space and you ask yourself the question, how much energy is there in that cubic centimeter of empty space? According to general relativity, there's no reason why the answer has to be zero. The energy density of empty space is a constant of nature. It could be negative, it could be positive, or it could be zero. That number, whatever it is the vacuum energy. So the hypothesis that that energy is the correct value to explain 70% of the critical density fits with the hypothesis that that is the dark energy. The dark energy is, in fact, the energy density of empty space, the vacuum energy. This is the same thing that Einstein was talking about when he first invented what he called the cosmological constant. Einstein added this term to his equation, as we will talk about later, because he was not able to explain a static universe within his theory. We now know the universe is not static, so Einstein said that was a great mistake of his, but now we're bringing back the cosmological constant. It's exactly equivalent to this idea of vacuum energy. So that's a very good idea. We don't need to complicate the idea that the dark energy is vacuum energy, inherent in empty space, plus our ideas about dark matter and ordinary matter are enough to fit the data. Why then do we even contemplate other possibilities? Well, there's one point, which is that we were just surprised. We were very surprised with the existence of dark energy itself. We had a preference, we had a prejudice ahead of time that matter made up the critical density, and we were wrong. So our prejudices about what ideas are simple and make sense shouldn't be taken too seriously. We're keeping an open mind about this possibility. In fact, just like the flatness problem, there are sort of naturalness and fine-tuning problems associated with the concept of a vacuum energy. One is called the cosmological constant problem, which is just the statement that once you admit there can be vacuum energy, you can start asking how big should it be? The answer, as we will see, is that it should be much bigger than what we would observe. Once you admit that there can be any energy density in empty space, the surprise is that it's so tiny. The other problem is called the coincidence scandal. The coincidence scandal is an exact analog to the flatness problem. Remember, the flatness problem said, look, the energy density of stuff decays away very quickly. The energy density in the equivalent of the energy density in the curvature of space decays away slowly. Why would it be the case that we are born right at the right moment when these two things are comparable to each other? These two things evolve with respect to each other, the spatial curvature and the energy density. Wouldn't it be a coincidence if there we were at the right time to observe both of them? This kind of argument convinced people that the spatial curvature must be zero, that we must live in a flat universe. That turned out to be right. But exactly the same set of words applies to the vacuum energy. The vacuum energy doesn't evolve at all. As a function of its energy density, it doesn't change as the universe expands. It doesn't go up or down. But the energy density in matter or radiation does go down as the universe expands. These two numbers change with respect to each other by quite a bit. However, we're inventing a universe now, claiming that it fits the data, in which 30% of the energy density is matter, 70% is vacuum energy. Those numbers are close to each other. In the past, it was almost all matter. In the far past, it was almost all radiation. In the future, it will be almost all vacuum energy. Why are we lucky enough to be born at the right time when the vacuum energy is comparable to the matter in the universe? That's the coincidence scandal. I actually don't have any good ideas for why that might be the case. So we have a theory that fits the data. We keep getting more data, the theory keeps fitting. But we recognize that the theory we have has holes in it in the sense that we don't understand why certain parameters take on the values they do. That will encourage us to keep looking at more theories, at different possibilities, and in the rest of these lectures, we're going to take some of those very seriously.